First of all, thank you very much for inviting me to this. I do feel slightly intimidated because Jeremy Butterfield was my PhD supervisor and John Barrow was my examiner, so I do feel as if I've returned to my youth in a way. I've put this first slide up really to indicate how broad this topic is. It touches on lots of things. The physicists are going to have something to say about it, so too are the mathematicians, and indeed the little character at the end, just outside the box, the person who really thinks outside the box, the philosopher. And that really is how I'm going to divide the talk up. I'm going to divide it into a section about mathematics, a section about physics, and then a section about the philosophical implications. So what am I going to talk about? Well, I'm going to talk about a new kind of computer. It's a computer which is not a Turing machine, and it exploits the relativistic nature of space-time to perform non-Turing computable tasks. I'm doing that against a background of the orthodox idea, which is Turing's idea, which is that computations are performed using a Turing machine. And the idea that that concept is exactly the right one for our notion of computability is widespread. And so what I've put here, this is by Hao Wang, remarks. So he says, it's absolutely impossible that anyone who understands the question and knows Turing's definition should decide for a different concept. Now, if I put my philosophical hat on just for one moment, I feel very uncomfortable about that. Not necessarily because he's talking about Turing, but it's just this idea that it's absolutely impossible. And the reason why I'm uncomfortable about that is, or at least can be encapsulated in this poem from Emily Dickinson. And it's the idea that it's experiment that escorts us last. His pungent company will not allow an axiom an opportunity. So from the point of view of trying to find out about the world, you can't have axioms. What you have to do is you have to perform experiments, and it may be that certain axioms that you hold very dear will be lost. So there's nothing that is incorrigible. And for the philosophically minded among you, will recognize that that's essentially the idea of Quine, that there is no truth which is absolutely beyond revision. There may be experiments and new theories which will then mean that becomes either false or indeed obsolete. Okay, so that's my feeling uncomfortable about it. But I haven't put any meat on the bones, as it were, and I haven't shown you the particular experiment. So those are the four bits: history, the physics, mathematics, and the philosophy. Let me just say something about the history of this topic. I've just chosen there a few papers that were involved in this. So I guess it really started off with a very clever idea from Itamar Potowski. And I'll have a look at what that clever idea is, but it's basically, he had an idea about how to perform computations by exploiting the relativistic nature of space-time. It doesn't quite work, or at least it doesn't deliver what you really want it to deliver. But that was actually the clever idea. And then myself and David Malament got involved in this. And then after that, there have been lots of papers, particularly by John Ehrman and John Norton. And I think the person who's done the most interesting work in recent times is Philip Welsh, who's just over there, who's looked in particular at the pure mathematics of these new computers. And I'm going to try not to say very much about the pure mathematics because Philip tomorrow is going to be talking about exactly that. Now, for some reason, that diagram hasn't quite come out as it should. So here I'm just looking at the space-time of Newton. And so I'm going to take a completely classical look to begin with. And what I'm going to maintain, or what I would maintain uncontroversially, is that Newton's conception of space-time is basically the space-time of intuition. And so you have absolute time, which can be marked off like that, Monday, Tuesday, and so on. And observers, of course, just move through that, and they all agree on elapsed times and so on. Okay, so that's the background. And then in terms of computability, so as it were painted onto that, we have this concept of the Turing machine. Now, there are lots of different ways of characterizing a Turing machine. I don't particularly want to make it technical. I assume that you have some kind of picture in your own mind about what a Turing machine is. I borrowed this diagram from Roger Penrose's book, The Emperor's New Mind. So what we have is a finite state device, which is just that. And so the program resides in this finite state device, and it has access to an infinite memory, which you can think of as being a tape. So it's an infinitely long tape. And I suppose it is worth pointing out, perhaps even at this stage, that it's a pretty crazy machine. I mean, people talk about Turing machines as if they have one at home, but they don't. They have a much smaller version of these things. And I think as I go on, I will be emphasizing that, particularly when you will begin to have reservations about the machines that I'm talking about. I'd like you just to remind yourself that actually this thing is crazy. Okay. I also need a computer user, and normally one doesn't talk about the computer users, but the role of the computer user is going to be crucial in what I say. So that's my computer user. And I'm just going to look now at how we think about computing. Perhaps we don't think about the space-time structure when we're thinking about computing, but if we did, then it would be the space-time of common sense. And so there I've popped in the space-time of common sense. So that's just Newton's space-time, Newtonian space-time. And so what I have on the right-hand side of the diagram is a Turing machine, and I've set it a not particularly taxing problem to add 2 and 2. And the way it does it is that it will run through the program for a while, and then at some point it finds the solution. Say there, it finds the solution, and then what it does is it signals to Homer, the computer user. So it signals and it tells him that the answer's 4. I apologize because this is pretty obvious, right? But you'll see the point of this in a second. The problem with this, or maybe it's not a problem, but if I phrase it in this way, then you might say, yeah, I know a bit of physics, and actually the space-time isn't like that. So even though you've got this concept of Newtonian space-time, it isn't really like that. So what is it like? Well, first approximation, you might say, well, it's more like Minkowski space-time. So one of the features of Minkowski space-time, of course, this is early Einstein, of course, 1905. So one of the features of this is that that elapsed time becomes relativized to a world line. So it depends which world line you're moving on. And as we all know, the faster you travel, the slower or the smaller the elapsed time. And that, of course, gives rise to the twin paradox. So with the twin paradox, as probably most of you already know, you start off with identical twins. They're the same age. And what you do is you allow one of them to, the stay-at-home twin will travel on this world line, and then there's a traveling twin who speeds out, presumably at very high speed, and then speeds back again, and they meet up. And if they do that, then the stay-at-home twin on this world line will have clocked up more proper time than the travelling twin. Okay. Where's all this heading? Well, it's heading here. So this was Itamar Potowski's idea. Potowski said, you know, can we exploit this? Can we exploit this, the difference in proper times? And he said, what about having this? What about putting a Turing machine on the stay-at-home world line, and then have the computer user travel away and then return? And you can organize this in a way that you can make this time as small as you possibly want. So I've just made it a day. And what that would enable the computer user to do would be to have access to 1,000 years worth of computations, but just in one day. Okay? And what Potowski thought was that somehow you could use this to perform a super task, that you could perform an infinite number of computations in a finite time using a setup like this. Unfortunately, that turns out not to be the case. And it's easiest to explain why that's not the case by just showing how it could be the case. The only way it could be the case is if you had a setup whereby the stay-at-home twin, as it were, travelled on a world line whose length was actually infinite. Okay, so that's what this diagram is supposed to represent. This length, the length of that line as measured, is infinite. This circle here is really just a cosmetic mark. So actually, this bit here is really the edge of space-time. Okay. The other observer, the computer user, so this is Homer, now takes a different route through space-time, and they travel to an event which is such that all these events lie to the past of it. And what you can do in a space-time like this is right off the bat, you can do something that's quite interesting. You could, for example, solve the Goldbach conjecture. So how would you do that? Well, one way you would do it is you would just get the computer to check whether 2 is the sum of 2 primes, and then 4, and then 6, and so it just goes through in a recursive way, going through all the even numbers to check if they're the sum of 2 primes. If it finds a solution, then what it does is it will signal to the solution event, which it can do because all these events lie to the past of the solution event. And so at the solution event, you would then have the solution. If, on the other hand, no solution is found, then no signal will be received at the solution event, and so that would mean that the Goldbach conjecture is true. So if you receive a counterexample, it's false, and if you receive nothing, then it's true. Okay, so that's quite interesting. Okay, so spacetimes that have these properties are known in the literature as Malamud-Hogarth spacetimes, and you're feeling a little bit short-changed because you're thinking, you know, he's just drawn a picture. What I want to do is I want to see one of these things. Okay, so it's quite easy to construct one of these things. So to construct a toy one, for example, so I'm not for 1 minute trying to sell you this as a realistic solution. It's not a solution to the Einstein field equations, for example. So what I would do is I just take ordinary Minkowski space-time, and it's not going to work in Minkowski space-time, but now I'm just going to do a little bit of surgery. That's what I'm going to do. So what I do is I just identify a point P, and I just make a little cosmetic mark around P. So this is just some compact region. And then, so outside here we just have the usual Minkowski metric, and inside there's the Minkowski metric. But now what I do is I introduce a conformal factor. So inside there it's just going to be omega times the usual times the usual Minkowski metric. And I fix it so that, it's also omega squared times the usual Minkowski metric outside as well. But I fix it so that omega squared is equal to 1 in the region outside the circle. And inside the circle, I have it so that omega squared tends to infinity as I approach the point P. Okay, now if I do that, then what I'm actually going to get is something which is not a space-time because the metric is then badly behaved. So having done that, having made the metric blow up as you go towards P, I then remove P. Okay, so I then take it out. And if I do that, then what I'm left with is one of these Malamud-Hogarth space-times, because if I choose a point down there, then a world line like that, a time-like world line like that, is going to be infinitely long. So if I measure the proper time on here, it's going to be infinitely long. And all of those events lie to the past of some other point. Okay, so that's a Malamud-Hogarth one, and maybe it's not that impressive, but it shows that it's at least possible. When people were playing with these, initially, it was pointed out that there might be something paradoxical about these kind of setups where you have computations, where you're actually doing things in space-time, in space-times with a structure like this. And it was pointed out by John Norton. You might have a situation like this. What about if I had a lamp that was on for the first second, and then was off, and then was on, and it was being watched from the point P, so it went on, off, on, off. Then you can ask the question, from this point here, will the lamp appear at the final moment? Will it appear to be on or off? Now, the philosophers among you will probably recognize that as being a relativistic analog of a problem that's already been around. It's called the Thompson lamp. Okay, so what you have with the Thompson lamp is you have a lamp which is, okay, so with the Thompson lamp, you have the lamp on at t is equal to 0, and then off at t is equal to a half, and then on at t is equal to 3/4. This whole experiment takes place in 1 minute. And what I'm doing is I'm dividing the remaining time by 2 each time. So it goes on, off, and the whole thing is speeding up. And the question is, at t is equal to 1, is the lamp on or off? And there seems to be some kind of paradox, because any argument that you're going to give for it being on is also going to apply to it being off. Now, fortunately, there isn't a paradox involved in this. And actually, once you realize that, you realize there isn't a paradox involved in this either. The reason why there isn't a paradox involved in this was pointed out by Benacerraf. And it's simply that, well, the way he phrased it was he said, look, what you've done is you've told me a story between 0 and 1, but excluding 1. So what actually happens at 1 is not determined by your story. In other words, whatever happens at 1 is entirely consistent with the story that you've told before. So actually, in asking, is it on or is it off, you're not asking the right question. You'd have to put in some further constraints that cover 1 before you'd be able to answer that. Okay, exactly the same kind of argument shows that in these MH space-times, there also isn't a paradox. Okay, let's make it a bit more exciting. I think solving the Goldbach conjecture is perhaps not that exciting. But here, you can see that actually, not only can you solve things like the Goldbach conjecture, you can actually solve problems which are genuinely unsolvable by a Turing machine. So to pick the simplest one, the halting problem. So everybody knows the halting problem. It's the problem of if you're given an arbitrary Turing machine, can you decide whether it's going to halt or not? There is no Turing machine that can make that decision. The halting problem, on the other hand, is decidable in this MH time setup. And all you do is you just... I don't know how that happened. All you do is you just arrange for the Turing machine, which is travelling on this line here, you arrange for it so that if it does halt, then what it does is it will send a signal to the solution or MH event. So it sends a signal there saying, yes, I've halted. So if the computer user travels to the MH event, looks for the signal, if there is a signal, then that means the machine halted. If there's no signal, then that means that it didn't halt. So that's a way of deciding the halting problem. Okay, let me say a word about the physics. I think when I say the physics, I suppose what I'm really saying is our universe MH? And if I'm asking that question, then really what I'm doing is I'm appealing to solutions of the Einstein field equations, and I'm asking the question, are those solutions MH solutions? What do I want to say? Well, I want to say that some of them are. Okay, so if you look at the Reisner-Nordström solution, for example, then that turns out to be MH. In fact, I can probably show that roughly. The trouble with space-time is it's quite big, and so the only way to really get it onto a board is to draw it using a Penrose diagram. So everything's shrunk down, but it's shrunk down in a way that it's infinitely shrunk down, but it's done so in a way that preserves the causal relations between the events. So in the case of the Reisner-Nordström solution, what is effectively happening is you have, as it were, a series of universes. So this is one universe, and this is another, and they're joined by a throat. And the way that you would set up the MH kind of setup is you'd start the machine there, and then you have it just compute and compute and compute. It looks as if this is finite, but this is a Penrose diagram, so actually that isn't finite. If you measure the length of that, then it's going to be infinite. And you then just get the observer to move into the throat that joins this region with that region, and as soon as it gets to a point like that, then it has all the computations in its past. So the Reisner-Nordström is an MH solution. Some of the Kerr ones, rotating black holes, also turn out to be MH, and Ante de Sitter in its universal covering form is also MH. There are bound to be people in the audience who are already thinking, yeah, all those solutions you've picked are not great solutions. It's true that I concede that this solution to the Einstein field equations is probably unstable, and perhaps the Kerr ones are too. What I'm really pointing out, I suppose, and we've already heard something about the cosmic censorship hypothesis, MH spacetimes all violate the cosmic censorship hypothesis. Penrose's strong version, because none of them are globally hyperbolic, so you can show that none are globally hyperbolic. They also, they might, in some cases, possess infinite blue shifts. You can get around that. Garrosh has shown how you can have an MH setup which doesn't necessarily have the infinite blue shifts. That's all I'm going to say about the physics, because for reasons that I'll come on to, in a way, in terms of my conclusion, it's not terribly important. Okay, what about the mathematics? I'm not going to say too much about this because I have a suspicion that Philip is going to say much more tomorrow. I will just say that the setup that I had, this simple setup, so I'll just go back to the toy setup. So a setup like this, what I do is I call that a SAD computer. It's a SAD computer of order 1. And the reason why it's a SAD computer of order 1 is because it can decide sentences in arithmetic with one quantifier. So it can decide things like that, and it can decide things like that. Okay, so sentences with one quantifier, and you can see how that works. If you're doing there exists, then you just check. You would just put x equal to 1 there, and 2 and 3. This is a recursive relation, so you can just go through them one after the other. If it finds a solution, then it signals the solution. And there's a similar but different setup which is used to decide that. Okay, so yeah. It turns out, and this was shown by Ehrman and Norton, it's not really a difficult argument, that SAD1 cannot decide sentences with two quantifiers. So if I'm considering sentences like this, for example, then it can't decide it. In general, it can't decide it. Well, that's quite interesting, isn't it? Because what we had for the Turing machine is we had problems that were decidable and undecidable, and likewise with the SAD1 setup we also have problems that are decidable, problems like this, and then some problems which are undecidable. Okay. You might say, what about more complicated setups? You know, all you've done so far, Hogarth, is you've just got this very simple setup. You might choose something that's a bit more complicated. We can do that. So we can consider, sorry, excuse the hideously complicated looking diagram. What's going on here is, this is a space-time diagram. This bit here is supposed to be a SAD1 computer. It lies to the past of another SAD1 computer, which in turn lies to, and so on. And we have an infinite number of these SAD1 computers. If you do that, if you string them together, then you can decide sentences in arithmetic with two quantifiers. Okay. You have to do a bit of work in setting this up, but you can do it. And having done that, it's much easier just to go away, stop thinking about space-time particularly, and just to draw these in the way that you might draw a Turing machine, so you just cut out all the physical detail. And from a pure mathematics point of view, if you're doing the pure mathematics of these things, then this is the way to think about them. So an ordinary Turing machine you can think of as, well, it's basically a computer that can compute forever, but the solution event, or MH event, is always going to have in its past only part of the Turing machine. A SAD1, on the other hand, has the entire Turing machine in its past, and a SAD2 is just a string of SAD1s. Okay. It's an infinite string of SAD1s. I'll draw it like that. And what do we know about these things? Well, you can keep going. So you can have SAD2s, but you can have SAD3s and SAD4s, so you just keep the thing running. And you can show that SAD-n can decide sentences with n quantifiers, so that's the positive result. And then the negative result, but it's a nice negative result, is that it can't decide sentences with n+1 quantifiers. In other words, these SAD machines map very neatly into the cleaner arithmetical hierarchy. And then finally, because you're feeling extremely adventurous now, having created all that, you can create the monster, and the monster is the add machine. So what you do with the add machine is you string together, first of all, a SAD 1, and then a SAD 2, and so if you're given a sentence in arithmetic with 4 quantifiers, for example, then you just send it to SAD 4 and it solves it and so on. And so you can decide all of arithmetic, which of course makes Gödel's theorem, well, you might want to reinterpret it. That's the mathematics. Let me just say something about the philosophy. I think, in a word, it's about a change of attitude. It's very, very difficult to change people's attitudes after the age of 21, I've found. This is tricky. So what I'm going to say, you probably won't buy. But I will say this. I have a different attitude and I get on very, very well with it. So if you want to give it a test run for a while, you too may find that it works extremely well. This is my attitude. First of all, I think there are lots of computers. There is no natural or ideal or given way to compute. That's maybe not particularly convincing as I've phrased it like that. But what I would invite you to do is to think about this with regard to geometry. So what I'm going to do now is I'm just going to present this as an analogy. I'm not for 1 minute supposing that computing is geometry. That would be silly. But the way you think about geometry, if you know something about geometry, is the way that you should be thinking about computability. Okay, so how do we think about geometry? Well, we think about it, first of all, we used to think about it as Euclidean geometry. So Euclidean geometry just captured the concept of geometry. And then something happened in the 19th century. New geometries, non-Euclidean geometries, Lobachevskian and Riemannian geometry were discovered. And there was then a period of tension. All forgotten now. We don't have this tension now, but trust me, people were tense. Okay, so during this period of tension, which is roughly 18th century through to 1915, we have, I think it's fair to say, what we have is individuals recognizing that there are other geometries, but nevertheless giving arguments for the supremacy of Euclidean geometry. That's what you have. So we have ideas already from Kant that Euclidean geometry is actually something we project on the world, so you couldn't even imagine the world as not being Euclidean. We have words you will find in the literature. Euclidean geometry is just natural, it's perfect, it's intuitive, it's ideal. And then things get really tense. So with Poincaré, he takes the first step, so he embraces the new geometries, but he says, okay, even though I think they're mathematically consistent and completely bona fide from that point of view, nevertheless we should take Euclidean geometry to be conventionally true. We don't have to consider those other geometries. We can always account for geometry using Euclidean geometry. And then we also have Russell, who again embraces the non-Euclidean geometries, but what he says is, well, I don't mind the non-Euclidean geometries with constant curvature. They're okay, but the other ones, they're beyond the pale. And he had basically Kantian reasons. Then what happened? After 1915, there was just a revolution, basically. And at a stroke, we started to think about geometry in a completely different way. Everybody who thought about geometry in a different way, and they basically thought about it as a two-sided concept. So yes, you have pure geometries, Euclidean geometry, Lobachevskian, you have Schwarzschild geometry, the black hole geometry, and then you have questions about physical geometry, and they're really questions for the physicists. So I suppose, obviously that would include general relativity, for example. Why am I saying all this? Well, I'm saying it because what I think has already happened to our notion of geometry is now happening with computers. So there is new evidence coming to light, evidence of the type that I've shown, but not just evidence from relativistic physics, also from quantum physics, also from people looking at mold computers, for example. And what I'm supposing is that we are actually now, currently, in a period of tension. It's like that period at the turn of the century. We don't quite know how to think about these things. What I propose is that the way to get out of the tension is just to think about computability as a two-sided concept. In other words, we have pure computability, where we think about the ordinary Turing machines, the way that Turing thought about it. Then we have SAD1, SAD2, we've got add machines, and some other machines that I don't even know about would be on this list. And then we have physical computability, a completely different set of questions, and there you're going to be looking at the physical theories that can accommodate these computers. So, for example, you would be looking at the cosmic censorship hypothesis if you wanted to assess just how realistic these MH computers are. It's kind of similar, isn't it? I know it's a rhetorical device to switch between the two, just to get you to think that they're very similar, but there you are. How does this work in practice? So what I'm doing is I'm just telling you now how I approach various questions that are the kind of questions that philosophers and others might ask. So what I'm going to do is I'm just going to remind myself how I answer questions about geometry. So somebody says to me, do the angles of a triangle sum to 180 degrees? If a student says that to you, then how do you answer that? Well, you say, well, yeah, they do in Euclidean geometry, but actually, no, they don't in Lobachevskian, and then you give a little list. And then you say, but actually, if you're talking about what do they do in the real world, then actually it happens to turn out to be no, because space-time is a bit curved. And then you've answered the question. Okay. I'm proposing that an analogous question, the counterpart question, if you like, in computability is the halting problem decidable? Now, typically, you would just say, no, it's not. What I'm proposing is that you should say, no, it's not by the ordinary Turing machine, but yes, it is by the SAD1, and then you give a list. That's from the pure point of view. I'm not considering the physics at all. And then from the physics, well, there's lots to say about the physics there, I suppose. If you were just concentrating on the SAD machines, then you would maybe look at, be talking about cosmic censorship hypothesis. Okay. Here's another question. So, isn't a SAD1 somehow less real than the ordinary Turing machine? So you get this into when people talk about these things, they feel it's less real. They think the ordinary Turing machine is a real machine, whereas SAD1 is less real. Well, I don't have an answer to that, except I would just answer it with a question. Is Lobachevskian geometry somehow less real than Euclidean geometry? Okay, so this might be the most important bit, because there are at least some people in the audience who are thinking already about Church's thesis. Okay. Let me talk about Church's thesis, first of all, by considering this statement here. The true geometry is Euclidean's geometry. And I've called that Euclid's thesis. He didn't have this thesis, but it was an idea that was around, and we saw during that period of tension it came out. That was Euclidean geometry really was the true geometry. And if you want arguments for that, then you will find things like it's pure, it's natural, it's intuitive. This last one is important, that there are different yet equivalent axiomatization. You can axiomatize it in different ways. It all converges on the same thing. That's a very, very good argument, right, for Euclidean geometry being the true geometry. I suppose you might say, you might argue against this. I'm not sure anybody did at the time, but you might say, actually, no, I don't think Euclidean geometry is the real geometry. It's actually spherical geometry. That's the real geometry. The point about this argument is that actually neither of those positions is right. We don't talk like that. You actually want to say that's just a pseudo statement. And in explaining to somebody why it's a pseudo statement, you'd explain all about this. You know, geometry is really a two-sided thing, and we think about it from the pure point of view, and we think about it from the physical point of view. Okay. The ideal computer is a Turing machine. Now, I'm not supposing for 1 minute that is your favorite version of the Church-Turing thesis. But for the purposes of this talk, it's fine. And any version of the Church-Turing thesis that you give me, I will be able to apply the same argument. At least I haven't heard one that this argument doesn't apply to. So what kind of arguments do you hear for this? Well, if you look in the literature, and you pick up any textbook on computability theory, you will find words like pure, natural, intuitive. This one's a good one. Different yet equivalent axiomatization. So in 1936 it was found that actually you could characterize Turing's concept in a variety of ways. They looked different. Superficially they looked different. They all converged on the same concept. That's fantastic evidence, isn't it, that the Church-Turing thesis could be true. Against, István Nemeti and his group in Hungary have actually argued against this. They've actually said, no, it's the SAD1 machine, that's the ideal computer. You know, their arguments are perfectly respectable. However, from my point of view, with my attitude, what I would want to say is that actually neither of these positions right. And the reason why neither is right is just because there is no ideal computer in the same way that there is no ideal geometry. Those people who study computability might be feeling quite uncomfortable about this because they might think, hang on, I really need the Church-Turing thesis. I invoke it all the time. What do I want to say about that? Well, what role does it actually play? I think it just plays two, but they're important roles. The first is it captures the concept of computability, so you know you're talking about the right thing. Okay, you know that the Turing machine is the right thing you should be talking about. And secondly, it serves as a useful heuristic when proving theorems. So you can just do a little bit of hand waving and you can say things like, oh, if it's intuitively computable, then it is computable by a Turing machine. And that works really well. It cuts down proofs enormously. But when you think about it, Euclid's thesis performed those two roles almost exactly. It captured the concept of geometry, so everybody felt that the thing they were talking about was in fact geometry. It also served as a heuristic, and you find this in Euclid's elements. Euclid's elements, actually, not all the propositions follow from the axioms. There's a bit of hand waving whereby if it's intuitively true, then it's true. And actually, it always is true. He doesn't make any mistakes. But what he's in fact doing is his intuitions are based on Euclidean geometry, so it's fine. The point about this is that in the case of geometry, we were able to get rid of Euclid's thesis. We don't have it anymore. And so much the better for it. In fact, you've never even considered Euclid's thesis. It's probably never even occurred to you. We used to have it, now we don't have it. And science gets on much better without it. All I'm proposing is that exactly the same kind of thing happens with the Church-Turing thesis. You can get on without it. So, for example, well, first of all, I've already claimed it doesn't capture the concept of computability. For number two, well, in all those cases where you filled in the detail by just saying it's intuitively computable, therefore it's computable, actually you need to fill those details in. You do need to fill them in. And that's what happens in Euclidean geometry. You actually need to fill them in. And I think on that point I will stop.